Hey everyone, welcome back to Ask Becca About Space. I am once again just sending you all the best from Norway. Kind of in the midst of this crisis situation, we in Norway have been taking our government recommendations really seriously. So I'm really excited to tell you that as of today, we're starting to soft open just a few things. Things like schools and universities will soft open next week for students who are finishing and need access to labs and things. So yeah, for the most part, we've been all trying to do our parts to flatten our curve in Norway. And because of that, after only 5 weeks, we can start to kind of loosen the guidelines a little bit. So I'm hoping for the same wherever you live. And there's at least a tiny light at the end of the tunnel. I don't think it's over for Norway. I don't think it's over for anyone really, but at least now we can start to kind of adjust ourselves and loosen ourselves a little bit. So that's good. Yeah, so I have a couple of more questions from Lillian, which I am psyched to get into. So let's do that. Okay, Lillian asks, what are some things we know about dark matter? This will be short because we don't know a lot about dark matter. Basically, we know a few things. We know it has to be there. We know that it's pretty much everywhere, but we can't see it. And we know that it's really hard to detect. Okay, so number one, how do we know that it's there if we can't see it? I guess this is both number one and number two. You can't really see it. How do we know it's there? So there is a concept called momentum. And momentum is basically a measure of how much mass something has, like how much stuff that thing has, and how fast it's moving, or something called its velocity. Okay, velocity is speed with a direction. Okay, so that means that it's a vector quantity. It's speed, but in some particular direction, whatever direction you want. It just isn't velocity if it doesn't have a direction. Velocity without direction is just speed. So momentum takes this mass quantity and this velocity quantity and combines them and helps us understand the way that object is moving. And momentum is something in the universe that has to be conserved. It has to be balanced, okay? And it's very telling of how an object is moving and how its mass or its stuff is distributed around the object, okay? So there's a scientist called Vera Rubin, and she was taking what we call rotation curves of galaxies. So she was watching the movement of stars around the centers of galaxies and looking at how those stars are moving in their orbits around the centers of the galaxies, okay? And what she noticed is that the stars aren't really moving in a way that would tell us that the majority of the mass, or that all of the mass pretty much, is in the center of the galaxy, where we see that it's most dense in luminous matter, or stuff that's not dark matter, or stuff that's emitting light. We see the most luminous matter in the centers of galaxies, right? But she noticed that that's not how the galaxies are rotating. That's not how they're moving. They're moving instead in a way that would suggest that a lot of the mass is on the outside of the galaxies, in those arms, on the outer edges of the disk. And that doesn't make any sense with what we see, because what we see is that most of the matter is concentrated in the center, and we have these kind of diffuse, wispy, kind of glittery spiral arms on the outside. But she found out that no, actually, there must be a significant amount of mass in the outer arms for a galaxy to be moving the way that it's moving. Otherwise, momentum's not conserved. And that breaks the laws of the universe, okay? So that means that there's a significant amount of something that we're not seeing, or at least we're not detecting with our eyes in visual light, okay? So since that discovery, there have been quite a few different theories as to what this stuff is. Because we see it, we can see it in the distribution of how the galaxy should look, but we can't observe it directly. And so for a little while, we thought, okay, well, there are a lot of things that we can't see because they're not emitting their own light. This is true in our own solar system too. We have planets that we can only see because we're close enough and they're reflecting sunlight, right? But if we're too far away, we can't always see those planets directly. There are stars that are really, really dim, called brown dwarf stars. They don't emit a lot of light. And so if they're really far away, there's a chance that we're just missing a lot of those brown dwarf stars. And so we thought, okay, maybe all of this dark matter is just a bunch of brown dwarf stars and just a bunch of planets, and that's all it is. But when you do the math and balance it out, it's too many brown dwarfs, too many planets. It doesn't make sense that we're missing that much mass in just things like brown dwarf stars. And so then we thought, okay, maybe this is a new type of particle then, something that doesn't really interact with anything besides with gravity, besides within a gravitational field. And that's kind of more or less what we think dark matter is now. We think that it's some sort of fundamental particle. It might be made out of things like protons and neutrons or something else, but we're not exactly sure yet. What we do know is that it's super hard to detect because it just doesn't react with anything, or it seems not to react with anything except through a gravitational field. Okay, so if you want to build a detector for dark matter, the thing that people have done is they've built a chamber far underground. Okay, and the reason they've built kind of a detection chamber far underground is because most of the stuff that's hitting the Earth in terms of radiation, particles, rays, things like that, that we're constantly being bombarded with but don't always feel because they don't interact with us, a lot of those things can be stopped by the ground or by several layers of concrete if you build a chamber deep enough, okay? The thing that it will not stop, theoretically, is a dark matter particle, because it is so weakly interacting that it can't be really stopped by a bunch of ground or a bunch of concrete in theory, okay? So any hope of detecting this kind of particle comes from underground chambers, basically. And so up until now, we haven't had a whole lot of luck nailing down what it is exactly. We just know that it has to be there, otherwise momentum breaks. Okay, so that's pretty much what I know. There may be some new things in the field since last I checked, but as far as I know, we're still not sure exactly what it is. But the idea is more towards some type of weakly interacting particle rather than just a bunch of brown dwarf stars and planets and stuff that we missed. Okay. Alrighty. Second question. What do the pictures in your background mean? Yes, these are actually, these are just a bunch of pictures of the sun taken in different kinds of light. Okay, so these pictures are from a satellite called the Solar Dynamics Observatory. And on board the Solar Dynamics Observatory, there are two instruments, what we call the Helioseismic Magnetic Imager, or the HMI, and the Atmospheric Imaging Assembly, or the AIA. And those two instruments primarily give us these types of images. Now, these are a little bit false colored because I think this photo is a little bit filtered, but they're false color anyway because they're just taken in a bunch of different bandwidths. But they tell us, because we're measuring the sun in a bunch of different wavelengths or a bunch of different types of light, they tell us different things about the sun. So for example, this one right here is what we call a magnetogram. And magnetograms tell us what the magnetic field of the sun at this layer of the sun that it's sampling looks like. And this is possibly not that great of an example because the sun has been a little bit magnetically boring lately. And so all these kind of salt and peppery yellow and teal dots, those are different foot points of magnetic field lines. But since the sun is a little bit magnetically quiet when these pictures were taken, there's not a whole lot to see. Kind of the same with all of these. This red one here, this is taken in a wavelength that is corresponding to helium-2. And what it does is it measures the lower solar atmosphere, and you might be able to see some kind of like wispy, cottony things. If you look around the edges, there's some things kind of sticking out of the sun. That is hot plasma sticking to magnetic field lines, and that's what we call a solar prominence. Okay. And then these two over here, they measure parts of the sun's atmosphere. These ones go a little bit higher into what's called the sun's corona, which is a word we're hearing a lot lately, but it's actually the name of the sun's atmosphere because it translates just to the word crown, right? So the sun's crown is the sun's atmosphere, the sun's corona. And when we measure the sun's corona, we can see what the atmosphere of the sun is doing and how it's reacting to its magnetic field there, which is basically what I do for my job. Is I try to nail down the sun's magnetic field parameters so that we can understand how the sun is magnetically moving energy into its corona. Okay. And then here though, in particular, you might notice that kind of black hole in the middle. It's not a black hole, but it is a picture of a hole in the corona that happens to be black in this wavelength. And what that means, it's also at the North Pole there. What that means is that the magnetic field is vertical with respect to the sun's surface there. So it's perpendicular to the sun's surface, and in the case of this coronal hole, which is what we call them, coronal holes, that magnetic field is pointed straight at us. Okay, and so that means that it's possible that some of the plasma of the sun, if it sticks to those magnetic field lines, and if there's enough magnetic energy for an eruption, like a solar flare, that plasma can follow those field lines out into space towards us. And then we could possibly get a geomagnetic storm, northern lights, and things like that. Okay, so these are all pictures of the sun just taken in different kinds of light. And if you would like to see the sun in almost live time, you can log on to the Solar Dynamics Observatory website through NASA, and I'll put the link down in the description for you so you can see the sun as it is today. Okay? All right, last question. I like this one because I'm a diva. So your mom texted me, she likes it when she can see your tattoos. Is that a constellation on the top of your arm? Well, yes, it is, Lillian. I like my tattoos too, which is great because they're permanently etched into my skin. But yes, so this one is the Big Dipper. I don't know if it's going to show up backwards in the video, but that's fine. And then this one's the Little Dipper. And then we have the North Star here. And then, oh no, okay, here we are. And then we have, oh, this is difficult with the background. This is Cassiopeia. So this is kind of the north sky part of my constellation arm project. It's kind of a ridiculous project because it's hard to project the sky onto like a cylinder that is your arm, but I tried it anyway. I think it's cool. So this is kind of like my north sky where we have the Big and Little Dippers and then Cassiopeia here. But then I also have like a little bit of the southern sky here. I have this tattoo of Orion. It's a little bit of our own kind of rendition of Orion, but I have this one as matching with one of my aunts, which I think is fun. And then these, okay, so everyone just kind of thinks that these are those like fun spirograph designs from that toy like from decades ago, where you can stick your pencil in and then it swirls around in these kind of geometries. And it is that, but it's also something else. So these two things are relative planetary orbits. This one is a relative orbit between Earth and Venus, and this one is a relative orbit between Earth and Mercury. And what that means is if we were kind of floating above the solar system and looking down at it, and if we were tracing the motions and orbits of Venus and Earth throughout time, or Earth and Mercury throughout time. Eventually, after several orbits, they would start to make these patterns relative to one another. And this isn't special for just Mercury and Venus. This is true for all of the planets relatively. They're all kind of orbiting at relatively the same rate every time. And so the difference between relative rates in those planets traces out geometric patterns like these. Okay. And then I guess these ones are also astronomy related. Lillian, you may remember when your mom worked at Badlands National Park, I worked at Badlands National Park too as the resident astrophysicist. And part of the job was to tell people a little bit about not only the sky local to South Dakota, but some of the local cultural stories relative to South Dakota. And in the Lakota creation story, this on my middle finger here is how the Lakota draw stars, basically. So we kind of usually draw stars as those kind of 5-point or asterisk things, but what's important to Lakota culture is that everything that's in the sky is reflected with everything that's on the ground. And so they tend to draw stars as a reflection glyph. And the constellations in their constellation wheel are a direct map of some of the geological features like the mountains and Devil's Tower and things like that on the ground. Okay, so kind of everything about the star creation and the creation story and star theology is based on the idea that things in the sky are reflected by things on the ground and vice versa. And then these two I got after I saw the solar eclipse in Nashville in 2017, which was real cool. And since everybody thought that everyone would go to Nashville, nobody went to Nashville. And I've never seen Nashville so quiet. And so it was actually really fun and really easy to get a good spot downtown and just kind of wait for the sun to go into totality. And then we all sat out on the grass and watched it. And it was like so amazing. And during totality, the street lights actually did come on and everything kind of went dark for a while. And then we saw kind of the Bailey's beads around the sun as the sun continued to come back. And it was just a really, really cool experience. So if you've not had the chance to see a solar eclipse, I would definitely, when things kind of return to a point where we can travel, I definitely recommend traveling to go and see a solar eclipse along the line of totality next time that happens. Okay. And I think those are pretty much the star related tattoos that I have, or at least the ones that I can show you. Okay. But anyway, thank you, Lillian, for your questions. I appreciate them so much, and I've had a lot of fun talking to you. As always, feel free to send more questions as they arise, and I will talk to you guys in the next video. Until then, I hope you are well. Okay? Bye.